few lectures ago, I introduced methods to build sequential logic using System Verilog. To quickly recap, sequential logic is logic that contains memory, and System Verilog offers a concise way to represent sequential logic. Any always statement whose sensitivity list doesn't include every signal that appears as an input inside the always block. In other words, on the right-hand side of an assignment or in a conditional expression. That will imply sequential logic. Likewise, any always statement that doesn't assign all possible outputs in every execution path also creates sequential logic. But in this prior introduction, I only described how to build simple clocked logic circuits such as flip-flops, counters, and clocked Boolean logic, and the purpose of that was to give you enough information to begin Project 1. This time I'll provide a more formalized discussion on sequential logic. First, let's cover some terminology. Sequential logic circuit, in general, is a logic circuit that contains memory. The only type of sequential logic that we will design this semester are synchronous sequential logic circuits, which is a sequential logic that is synchronized to a clock. I often use the word state to refer to the value of a signal at any point in time, but with respect to sequential logic, state is the information about the circuit necessary to explain its future behavior. In other words, state is the contents of the circuit's memory, or more precisely, it's the values that are stored in the circuit's internal flip-flops or latches. Latches and flip-flops are considered state elements, each storing one bit of state, and incorporating one or more state elements in a circuit allows it to remember the recent sequence of input values. And of course, the more bits of state, the more history the circuit is capable of remembering. The clock signal is responsible for synchronizing sequential logic, but sequential logic can respond to either the clock's level, in other words, whether it's high or low, or its edges, in other words, its rising or falling edge, which rising edge is the transition from 0 to 1, the falling edge is the transition from 1 to 0. Logic circuits that synchronize to the clock's level are called latches, and those that respond to the edge are called flip-flops. A latch acts like a combinational logic circuit when the clock is at a certain level, such as high. In other words, when the clock is high, the circuit's output is a function of its inputs, and the output will change immediately, or rather after the internal combinational delay of the circuit, in response to any input change. So stated another way, when the clock is high, the outputs respond to inputs right away. They respond asynchronously. They don't depend on a clock. They're independent of a clock. But when the clock is low, the circuit's outputs are frozen, maintaining their state from when the clock was last high. As I mentioned in the previous lecture, when I introduced sequential logic, latches are almost never used intentionally, at least not in FPGA design, and are sometimes inferred from badly written or buggy HDL code as an unintentional behavior. And I admit I still do that all the time as accidentally. Latches aren't used intentionally generally because latches make it unnecessarily difficult for the design tools to analyze the timing of a circuit and enforce the dynamic discipline, which I'm going to cover in a future lecture. Flip-flops, on the other hand, sample their input on the rising or the falling edge of the clock. Now, Why the rising or falling edge? What is significant about that? They do this because the time it takes the clock to transition from 0 to 1 or 1 to 0 is much shorter than the time the clock is high or the time the clock is low. I like to think of it as taking a photograph, which freezes the action during the time the shutter of the camera is open. In this scenario, the shutter time is the rise time for the clock signal. So in other words, you want the capture time, the shutter time, to be as small as possible to capture action, to freeze action. Flip-flops can be arranged into a group of flip-flops that stores multiple bits and collectively outputs a multi-bit signal. And this is usually called a register, but it's a little confusing because you also have the notion of a register in assembly language, which is an addressable memory location in the register file, which in the register file is a RAM. So there's a register, which is a multi-bit flip-flop, and there's a register that is an architectural concept in assembly language. I'm referring, of course, to the multi-bit flip-flop. The two most common types of synchronous sequential logic are pipelines and finite state machines. Pipelines are a method, very common method, to break up long chains of logic into multiple cycles where the intermediate results are calculated each cycle and captured into registers. This allows the logic to achieve high throughput despite having long latency. Now, when I say high throughput, I'm referring to the rate at which new outputs are produced. That can be very fast, despite the time it takes to calculate one result being very long. So you could think of this like a car assembly line. Once the assembly line is filled, a new result can be produced at an interval that is less than the total time required to produce one result after receiving its inputs. In other words, a car assembly line may produce a new car every 5 minutes, but it takes longer than 5 minutes to produce a car. The time the car was in the assembly line would of course be much longer than 5 minutes, but once that assembly line is filled, the throughput, the rate at which new cars are produced, can be once every 5 minutes. Finite state machines, on the other hand, are essentially like having a Boolean expression that can change each cycle depending on the circumstances or depending on the sequence of inputs. They're useful for use as controllers, such as controlling an ALU that requires multiple cycles to perform an operation. In that sense, this would be referring to an ALU that might take, say, 10 cycles to perform a divide, but can only perform one divide operation at a time. State machines can also be used as interfaces for arbitrated buses, or logic that, for instance, processes network packets. Now, the reason why you need one for that is because packets are usually received in pieces, and each piece of a packet needs to be handled differently depending on which piece is received. So as the packet rolls in, it may take multiple clock cycles, and the interpretation of each one of those pieces is different in each clock cycle. A finite state machine has a set of inputs, a set of outputs, much like any logic, but it also has state. For example, assume we want to build a finite state controller for a traffic signal at the intersection of two roads called Academic Avenue and Bravado Boulevard. Of course, this is an example from the textbook. Now, Academic and Bravado were named because they start with A and B, so you can think of that as Road A and Road B. The inputs to the state machine controller could be TA and TB, each of which is set to 1 whenever traffic is detected on Academic or Bravado respectively. So if there's a a car rolling through the intersection on either one of those streets or waiting at the light, those signals would indicate that. The outputs to the controller could be LA and LB, each of which 2 bits, because they indicate the state of the traffic light on each street at that intersection. So they would have a code for green, yellow, and red for the signal on each of each of the roads through the intersection. The controller could then be in one of 4 states. Two of the states would be green light for academic and red for bravado, or vice versa. In the other 2 states, you would have a yellow light for academic and red for bravado, or vice versa. A finite state machine can only be in 1 state at a time, 1 state per cycle. So this guarantees that there'll never be a green light on both streets. It's impossible, because the only way for that to happen is to be in more than 1 state at a time. We can name the states whatever we want to name them. We can give them symbolic names. In this case, we'll call them S0 to S3. So we can refer to those names while designing the circuit. Second thought, it might be better to call them green academic, yellow academic, green bravado, yellow bravado, but those names are too long. So we'll go with S0 to S3. Now, pairs of states can have an arc between them. Not all have to have an arc between them, but certain pairs of states can have arcs or arrows that connect them. And these designate an available transition from one state or another, or the ability for the current state to switch from the current state of the machine, rather, to switch from the originating state, in other words, where the arrow is coming from, to the destination state on the clock edge. If the condition, and this only happens if the condition on the transition is true on the clock when the clock edge occurs. There's a special arrow that has no source that points to the start state, which is the current state that is assigned to the machine after the machine is initialized, after it's reset. This used to be called a sanity state because it gives you an initial condition for the state machine. The state diagram can be shown as a graph with states and edges, or it can be shown as a truth table, which is possibly a little harder to read, but the table would be mapping the source state and the input values to the next state. So when representing a state machine as a truth table, what you're really doing is showing one row per transition that would appear in the graph representation. So in the graph representation, each of the edges, each of the lines, each of the arcs, each of the transitions would have a row in the truth table. So getting back to the example, in this case, when the current state is S0, meaning that academic has a green light, the next state will continue to be in S0. In other words, there will not be a state change. We'll stay in state 0 for multiple consecutive clock cycles as long as we detect traffic on Academic Boulevard, meaning that TA is 1, input TA is 1. And this will be regardless of the traffic on Bravado. So in this case, TB is a don't care. But when there is no traffic on Academic, meaning that all the traffic is passed and there's no more activity on that street, meaning that the TA input would be 0, we should begin the process of switching the Bravado light to green. This will happen in this design, in our design that we're building. This is going to happen whether there's traffic on Bravado or not, meaning that the TB is a don't care, still a don't care. For this situation, the next state will be S1, which is the yellow light on Academic. In the S1 state, we indicate a yellow light on academic and a red light on bravado. We will stay in this state for just one cycle, meaning that the next state is S3, regardless of the inputs, meaning that both TA and TB are don't cares. This would suggest that the clock period, the time between two rising edges of the clock, is set up to be whatever the interval is for the yellow light. So if we want there to be a yellow light for 10 seconds, then the clock period then must be 10 seconds. If the clock is faster than that and we still want to be in a yellow light state for 10 seconds, we would have to either need multiple yellow light states that we would have to walk through, or we would have to have another input that would be a timer, a 10-second timer that we would use together with this state machine as another input. But in this case, we're taking the simplistic approach where the clock cycle is assumed to be a yellow light interval. In S2, we are indicating a green light on bravado and a red light on academic. As with S0, we will stay in this state as long as we sense traffic on bravado, meaning that TB is 1, TA is a don't care. By staying in this state, I mean that the next state is S2, which is the same as the current state. So this is a loop back transition, just like we had in the case of state S1. Now, obviously, this design is flawed in the sense that as long as there's traffic on bravado, we will never switch to a green light on academic, meaning that academic could be starved. But again, this is a trade-off that we're making because we want to make this state machine simple. However, when in S2, if there is no indication of traffic on bravado, meaning that TB is 0, we will begin the process of setting academic to green by setting the next state to S3. Now, one thing I want to point out is that the TB value may transition to 0 and then back to 1 before the clock edge. If that's the case, the state machine will never notice that TB ever went to 0. In order for us to switch to state S3, TB must be 0 on the clock edge. In the S3 state, we indicate a yellow light on bravado and a red light on academic, and we will stay in this state for only one clock cycle as before when we had a yellow light on academic. Now we have our state machine design. We have to convert it to hardware. To convert the state machine to hardware, we need to associate a binary value with each of the 4 states. And since we have 4 states, we need at least 2 bits in order to associate a unique binary value for each state, although there's nothing that prevents us from using more state bits. As a matter of fact, in many cases, designers like to use 1 state bit per state so they can use 1 hot encoding, meaning that every state value has 1 bit and the rest 0 bits. But in our case, we'll use a binary, a simple binary assignment of the states. So we'll associate the values 0, 0, 0, 1, 1, 0, and 1, 1 for S0, S1, S2, and S3 respectively. The only state code that we can't change is the start state, which always must be zeros. Since the reset signal will reset the state register to 0. Of course, unless of course we use some special type of flip-flop or a non-traditional flip-flop design that doesn't reset to 0. But in general, flip-flops reset to 0. So our state value of zeros will generally be associated with our start state. And we want to ensure that we return to the start state when that happens. And also, by the way, whenever a flip-flop is powered on, it's going to come up in a random state, which is the reason why we need explicitly to reset. We need a reset signal whenever we're using sequential logic. We'll refer to the current state using 2 state bits, S sub 1 and S sub 0 for the first and second bit of the state. Don't get this confused with S3 to S2, S1, and S0, which are the state names. So we have S sub 0, S sub 1, or S sub 1, S sub 0 is the most significant and the least significant bit of the state, the current state. We're going to refer to the next state, which is the value that we will assign to the current state on the next rising edge of the clock, as S prime sub 1 and S prime sub 0. So we have S sub 1, S sub 0 is the current state, S prime sub 1, S prime sub 0 is the next state. This allows us to create our truth table, in which each row of the truth table is a transition, and where the inputs of the truth table are the current state, S sub 1, S sub 0, and the state machine input bits, which are TA and TB. And the outputs of the truth table are the next state bits, which is S prime sub 1, S prime sub 0. Once we have that truth table, we can convert the output columns to Boolean logic as you would for any truth table. Remember that you can ignore input entries that are don't cares. So in this case, S prime sub 1 is true on rows covering 3 implicate values, not S sub 1, S sub 0. S sub 1, not S sub 0, not TB. S sub 1, not S sub 0, TB. We can use the distributivity theorem to extract not TB or TB, and then eliminate that clause due to the complement theorem, and then convert the remaining expression to a simple XOR, since it's true whenever exactly one of S sub 1 and S sub 0 are true. S prime sub 0 corresponds to 2 implicates, not S sub 1, not S sub 0, not TA, and S sub 1, not S sub 0, not TB. A finite state machine then is built around the state register. The state register, like any register, potentially changes on every clock cycle. The output of the combinational logic that we just built, which is the next state logic, is fed into the input of the state register. So where we see the S prime sub 1 and S prime sub 0, those are the inputs to the state register. The inputs to the next state logic, again, that we just built from the truth table, is the output of the state register and also the inputs, the top level inputs, TA, TB. So stated another way, the input to the state register is the output of the next state logic, and the output of the state register is the input to the next state logic, as well as to the top level input. So you can see we basically just have a cycle here. Now, if the reason why this is allowed is because the cycle is, part of the cycle is the state register. It's been broken up by a sequential logic element. We need to convert the symbolic output values, green, yellow, and red, which are set to the outputs LA and LB, to binary values, 2-bit binary values. So we have LA and LB, which are outputs. They need to be split into 2 bits each. So we'll have LA sub 1, LA sub 0, LB sub 1, and LB sub 0. Then we can build another truth table that will associate the current state with the values of LA and LB and convert this state table to Boolean logic. So when drawing this as a schematic, we can collapse the 2 flip-flops that comprise the state register as shown here. Notice that the inputs are the next state, S prime, and the outputs are the current state, S. Also notice there's a reset input that resets the state, and of course the clock that synchronizes the circuit. We can now add the structure corresponding to the Boolean logic of the next state function, the next state logic. In this case, we can create a gate for each of the logic operators that we derived from the truth table. In this diagram, we'll use input bubbles to denote complemented inputs on any of the gates. We can then add our output logic, again associating one gate for every Boolean operator in the Boolean expression we derive from the output logic truth table. When we simulate this circuit, our test bench needs to provide a clock signal, a reset pulse, and the input stimulus for TA and TB. Each is a single bit. After the reset, the circuit will come up in its start state, in which it will generate a green light on academic and a red light on bravado. At this point, the inputs indicate that we have traffic on academic as indicated by the 1 on the TA input, and no traffic on bravado as indicated by the 0 on the TB input. As long as we have traffic on academic, we will stay in that state, which can be seen when the bravado traffic light sensor turns on or lights up, becomes 1. But despite that happening, we're still staying in the S0 state. But eventually the traffic on academic lets up, at which point the next state immediately will become S1. Now, because the traffic on academic continues to be 0 until the next rising edge, at that point, the academic light will become yellow. So we will be switching to state S1 on the next rising edge. In other words, to switch to state S1, academic traffic has to be 0 on the rising clock edge. So again, if it had gone to 0 and back to 1 before the next rising clock edge, the state machine wouldn't have noticed it. Once we transition to state S1, we'll have a yellow light on academic for exactly 1 cycle before switching to state S3, at which point academic light is red and the bravado light is green. This will continue to be the case for, in this case, 2 cycles, which is when the traffic on bravado lets up. Now, traffic on academic was detected during that period as well, but that doesn't matter. The state machine was waiting for the traffic on bravado to stop. At this point, being that TB is 0 on the rising clock edge, the state machine enters the S3 state, its obligatory yellow light state for bravado, before and it stays there for 1 cycle before switching back to S0, where it will then stay until traffic on academic lets up, and of course stays let up until the next clock edge. So let's reproduce this design and this simulation using System Verilog. In System Verilog, we need an always statement for each of the state register, next state logic, and output logic. So I'll start with the module line. Now I need a way to encode the symbolic values for my states into binary values. For this, I'll use parameters, which you can think of as pound-defined constants in C. And the reason I say this is because parameters are constants that have to be determined at synthesis time. And they provide a way to customize modules when you instantiate them. Of course, you cannot change them after you have synthesized your design. In this case, we're going to use the parameters much the way we would with a pound-defined in C++. So we'll have parameters for our states and parameters for our light values. Now I'll declare my current state and next state signals, and then create the state register process, which is the only process in this design that will be clocked, because the state process is clocked, but the next state and output processes are combinational. Now I'll create my next state logic, which is combinational, so I'll use an always com for that. And now I will build my output logic, which again is combinational. Notice that the output logic is only a function of the current state, unlike the next state process, in which the next state process uses as inputs the current state and the top level inputs. Can I use the top level inputs in the output process? Could I use TA and TB in here? Yes. If I did that, this would be considered to be a mealy machine, as opposed to the one that we have here, which is a Moore machine. In this case, the output is fixed for every state. It can't change. Once you're in a state, you have a specific output as defined in that state, so it's a Moore machine. Now I'll create a test bench. I will use the test bench to drive all of the inputs, and I'll use the waveform to validate that it's working. And the reason I can do that is because I've got a waveform from the book that I can use to compare with my waveform. Of course, that only tests one specific set of circumstances, so it isn't necessarily a good test bench. And now we'll simulate, and you can see that, in fact, the output does match what we have from the book. Okay, so that's all we have for this lecture.